So it's really my pleasure to introduce Alberto Bartesaghi. So he's faculty at Duke in electrical and computer engineering, also in biochemistry. And so he's been really doing some amazing work and his team to develop different techniques for collecting tomography data. And so I think he's going to highlight the BISECT technique and maybe some post-processing pipelines that have stemmed in recent days. So thank you.
All right, good morning, everyone. Thank you, Liz, very much. I think this is very important to, this center has played a very important role in disseminating these technologies. I'm going to actually start by asking the audience a question. How many people know what this structure is here on the right? Okay, I see a few hands up. You want to guess, Liz? It's a ferritin. There you go. Great. Okay, I have another question, follow up to that. So was that done using single particle or tomography? Tomography, that's a good guess. But that's exactly what I wanted to illustrate. I mean, I think what's really exciting about tomography is these days you can't really tell whether it was done using single particle cryo-EM or tomography. This particular one was done with single particle because I was lazy. I didn't want to update that, but I'm going to show you something very similar that was done with tomography. But I think that just goes to show how far actually tomography has come, and that in particular the resolutions that can be achieved today are actually quite we didn't even think that it would be possible a few years ago. So I want to start by giving like a big, sort of like an overview, and just as a way of background. I'm a computational scientist, so I have most of my background is in image analysis, in particular for cryo-EM and cryo-ET. And what I'm going to be trying to do today in this talk is just going to give you like the very, sort of like highlights of the things that you can actually do with these techniques, because we're going to spend a lot of time during the other talks actually talking about the details. So hopefully this will just set the ground and give some motivation for why these techniques are so important, and what's the state of the art and what are the things that are actually coming. So you're going to be learning a lot about how to prepare your samples, create your lamellas, and then taking those to the microscope, and then hopefully doing some high throughput imaging. And I'm going to be touching on two things. One is how do you actually make the most out of your samples? So you're probably going to be working very hard on producing those just right lamellas, and probably lots of them. So how do you actually maximize the benefit and get good quality data as fast as possible? And then most importantly, how do you actually convert that into high resolution structures, which is the reason why we're doing this. And I'm going to start by highlighting that cryo-ET has traditionally been like a low throughput imaging technique. And I put out some statistics here from the Empire database, which actually shows sort of like the size of the different data sets have been deposited in the data bank. And you can see that most of them only have like 15 tilt series, right? So those are 15 tilt series. Today, it sounds like very small data sets. But these are the statistics. So there are some outliers. We have some that are in the order of 100, and then there's one at 255. And this is not completely up to date. It's probably like a year old. So what's happening today is now the size of the data set are actually gradually increasing. And I think this is the point I'm trying to make here, that in order for us to be, to get the most benefit out of this technique, we actually need to be collecting a lot more data than we were, a few years ago. Now, there are reasons why these data sets are so small, and you probably see that when you go to the microscope, just collecting a single tilt series can be very time consuming, especially if you do it properly, if you want to get high quality data. And it can take anywhere from 30 to 60 minutes, depending on how careful you are. And also these are very large data sets, so you need to have a lot of storage available. So that's just some of the ideas of, of the reasons why these data sets have traditionally been quite small. Now, if you don't have enough data, then you're off to a bad start, right? So your chances of getting to high resolution are actually quite small. And this is another graph, this time from the EMDB dataset, that shows sort of like the average resolution per year of structures obtained using subtomograph averaging. And you can see that in the last couple of years, we've been around like the 20 Armstrong mark, which is not very high resolution, obviously. And one of the reasons that we've been sort of like stuck there is because we don't have enough data, right? So single particle, we're data rich. We have lots of data. We can collect many, many micrographs, thousands of micrographs, and that actually increases our chances of getting to high resolution. So this is something that needs to change if we're going to push this technique to high resolution. Also, if you're looking at samples in situ, we're going to have a lot of heterogeneous samples, which is going to need even more data than we probably have in single particle cryo-EM, where the proteins are actually purified. So now we're looking at proteins in situ, so we'll probably need even more data than single particle if we really wanted to do this properly. So there's been several efforts already on how to actually try to speed up data collection. As I mentioned before, the traditional approach, if you use like a dosimetric or the Hagen scheme, you can spend 20 to 30 minutes or more, depending on how the conditions of acquisition, which is obviously too slow. And there's been some approaches that try to actually collect the tilt series as you're actually tilting the stage. That way, you can get a tilt series really, really quickly in 2 to 3 minutes, and this is the fast incremental single exposure technique from Grant Jensen. But you're sort of like giving up the data quality by doing that. You can collect data very quickly, but then you give up the quality because you're actually tilting the stage as you collect your images, and that's actually introducing drift, and it's actually not keeping the high resolution information intact as you collect the tilt series. So we were trying to also try to address that problem and by designing like a new way of collecting data that is not only high quality, but you can also do this very fast. So before I tell you about BISECT, there's a couple of challenges that are actually very important when you go to high resolution. And one is that traditionally, tomography, you use very large field of view, and you take the tilt series of your area of interest, and you kind of like need to have the tracking roughly right, but it doesn't need to be perfect. Once you go to high resolution, you need to be imaging at very high magnifications, and then tracking actually becomes very critical, because the moment you lose track of your area of your sample, then your whole tilt series essentially become useless. So you really need to be careful when you image at high magnification that you need to, your tracking needs to be almost perfect. So I know that movie is a little bit crazy, but so one of the things that we're trying to do is how to actually improve the tracking, and we have this like the two-step predictive tracking where we can actually now crank up the mag. So here the scale bar is 100 nanometers, and we can collect the entire tilt series, and the tracking is really, really good and allows you to keep most of the field of view within the area of the image. And again, I'm just going through the big ideas here without getting too much into the details. Now, the way we actually managed to accelerate data collection without sacrificing resolution was by using this beam image shift strategy, which we use routinely in single particle cryo-EM, which essentially you leave the stage, you don't change the stage, but you just tilt the beam, and then that way you can image multiple locations within a certain area without having to introduce any mechanical movements of the stage, and that includes translation and also tilting. And that actually is one of the reasons why traditional cryo-electron tomography is so slow, because you need to, all these mechanical movements actually introduce a lot of delay. So using this technique, you can actually image multiple areas for every movement of the stage. And that way you can essentially collect multiple positions on your grid in parallel. Right? So in this case, we use a 5x5 beam image shift pattern, where at every position of the stage, we actually take 25 images, then we tilt, we take another 25 images, and then at the end of a single tilting cycle, we actually have 25 tilt series. And then each of them will have very, very good tracking, and there will be no sacrifice in resolution because the stage is actually, very stable because we're making, fewer movements, fewer tilting movements and fewer mechanical movements of the stage. At the end of the day, this comes down to be 2 to 3 minutes per tilt series, which is actually very similar to what you can get with FICE, but now you can get the speed and you can also get the quality. So this is the BISECT strategy, so beam image shift electron cryo tomography, which we've been using for a couple of years now. Not all the parts are showing up, but we actually validated this. We collected on a test sample. This is a small 300 kilodalton complex. It's a purified sample because we did this for benchmarking, and we collected tilt series using BISECT. And we did all the processing downstream, so particle picking, 3D refinement, and we got to near atomic resolution, demonstrating that you actually keep high resolution information as you're collecting the data, and you can do this very quickly. In this case, was about less than 5 minutes per tilt series, and you can still get to high resolution. So this is already a couple of years ago, and subsequent to this, this BISECT technique was also applied for imaging lamella, some in situ samples on lamella. There's a couple of groups from Rado and Jorgen, 2022 and 2023, where they actually used this beam image shift strategy to actually image multiple areas of a lamella and then get high resolution structures that way. Now, there is one other element that I want to mention here. So this essentially allows you to collect data fairly quickly or much faster than before, and also have high quality data at the same time. There is another piece of work that I wanted to mention, which is relevant to this, which is SmartScope. This is another tool that we developed that actually uses AI-driven approach to actually help you screen these grids. And the whole point is to make data collection as efficient as possible, because remember, we're trying to maximize the size of our electron tomography data sets. So if you can streamline screening, that can actually go a long way. So tools like this have also are also available from other groups, and also from Thermo Fisher and others. And I think when you combine these like high, very efficient screening that you can do, like remote operation, semi-supervised, together with high throughput data collection, really is gonna give us the data we need to feed into the data processing pipeline, which I'm gonna try to talk next. Okay, so having a lot of data is great, but it's also very problematic. Right, we are not actually used to having big data sets. So until a couple of years ago, we didn't know what to do with all this data. We were actually stuck for a while because we didn't know how to process or push that through the pipeline. So in particular, if you come from a cryo-EM background, cryo-ET, it's a lot more involved. There's more steps. There's more things that need to happen in the right order. So that just makes data analysis a bit more involved, and you will see this in the other talks in the morning. But essentially, you need to worry now about doing tilt series alignment. You need to do this more complicated CTF estimation because your images are tilted. You need to reconstruct your tomograms. And a very fun part is that you need to now pick particles in 3D inside the cell, which I think there's a lot of challenges, but it's a lot of potential for developing tools in that area. Now, one thing that you need to think about when you're doing high throughput data collection is you need to talk about getting feedback as you're collecting the data, right? So you don't want to collect tilt series for 2 days and then realize that your data is useless. So you need to have some kind of mechanism that actually gives you feedback in real time, and that allows you to assess the quality of the data. You can maybe try out different imaging conditions like tilt scheme, tilt spacing, and so forth. You can, this way, as you process data, as it's coming out from the microscope, then that will actually save you time later because you only need to align tilt series once. You don't need to do that over and over. So if you do it during data collection, it will actually save you time, make it more efficient. And that will also make the use of the resources more efficient as well. So one of the first things that we needed to do when we did this BISECT technology was to develop tools to actually do this on-the-fly data processing. And this is from a large session of tomography that we collected over 1,000 tomograms. So if you look at one of the rows in this plot, each dot is essentially one till series. So now you start talking about, high throughput data collection, getting to the level of, the kind of the amount of data you need to actually be able to pull high resolution structures out of this in situ samples. Without getting again in the details, this is like a very broad overview of the things that actually happen during data pre-processing. You need to align your frames, you need to align your till series, and there's a couple of ways of doing that. If you're using fiducials, you can use fiducial-based alignment, or you can use correlation-based alignment if you don't have fiducials. Then you align your till series, you do this tilted CTF estimation, you usually reconstruct like a bin version of your tomogram to make it efficient. And then you can even do particle picking during data collection. That will give you a sense for how many particles you have, are you able to pick the particles, and so forth. So this is all like critical information that is very useful to get during data collection, right? For example, if you cannot align your till series, then your data is not going to be useful. So you better change your strategy or do something to change that. Because if you're not able to align your till series, everything else downstream is not going to happen. So this just tells you, right, what you're collecting. Okay, so I can build tomograms, all of my parameters are good, my signal goes to high resolution, I can see the particles, and so forth. So just to give you one example, and this is why I think particle picking in tomography is a lot more interesting and there's a lot more challenges. You can do things like geometric-based particle picking, where we have these like different levels. In this case, these are viruses, and then you're after, this is an immature gag of a HERK virus. So essentially, you have different steps to the particle picking that involve detecting your virions, segmenting the virions, and then looking for the location of these proteins, of the gag protein, on these three-dimensional shells. More recently, there's been like a lot of movement in the area of using deep neural networks to actually help you detect particles in 3D. I listed a few here. And these have actually been very useful, but they're also very time-consuming because you need to train them, right? You need to train these networks to actually pick your object of interest or your protein of interest. So we've been developing tools to actually try to minimize the amount of training that you need to do. Picking in 3D is not fun. I'm sure a lot of you have actually experienced that. So producing the labels to train these algorithms is actually very time-consuming. And if you have 1,000 till series, you probably don't want to spend a lot of time actually doing that. So we've been developing tools to try to minimize the amount of annotation so you can train these networks really quickly and then be able to run during data collection. So once you have your particles, obviously that's where the fun begins. You can actually extract those particles traditionally using subtomograms, and then you can combine those using subtomogram averaging. And hopefully, if you have enough of those, and if you can align them properly, you can end up with a high resolution structure using subvolume averaging. Except that these days we don't actually use or I guess I should take that back. Some people use subvolumes still, but most the field has actually transitioned to using 2D projections instead of using the subvolumes. And this is sort of like trying to leverage all the tools that have been developed for single particle cryo-EM and have them work for tomography data. So essentially, what we do is once we construct the tomogram and we pick the particles, we can actually go back and extract the raw 2D projections, and that gives us a way to convert those 2D projections into 3D structures using the raw data and skipping like all the intermediate steps of subtomogram reconstruction and CTF correction and so forth. If you do it this way, you don't need to deal with the problem with missing wedge because you're just using the data you're measuring. So there's essentially no missing wedge if you do it this way. Then you can do more accurate alignments because you're not relying on fiducials, for example, but you're actually using the signal from your sample of interest to do the alignment. And all of these things means that you can actually get to higher resolution. I wanted to just put like a snapshot of what's going on. How do you actually convert, right, your raw data that happens at the very beginning here from your raw till series? There is a sequence of steps that you actually go through solving the geometry that at the end of the day actually result here in that single projection being assigned a single orientation in 3D and a translation that actually contribute to the 3D reconstruction. And then obviously, if you have enough of those, you can actually get to high resolution. But these are all the geometric transformations that actually happen that are very well articulated because of the tilt geometry. And you can actually directly go from the raw data to the 3D structure by cutting through all the intermediate steps. And that essentially means that you're able to to recover high resolution information. So several years ago, we developed sort of this framework where you now have, for each of your particles, you have like a small tilt series. And then you cannot really use the standard tools in single particle cryo-EM to do the refinement because these images are harder to deal with because they're noisier. They have the dose per image is much lower. So that means that there's more potential for overfitting and for introducing reference bias. So there is a way that you can actually overcome that by imposing the constraints of the tilt geometry. And then essentially what you do is you have this set of projections that are actually related by the tilt geometry, and then you can refine them in 3D as was like a rigid body. And then that actually allows you to overcome all these issues with reference bias and overfitting, and allows you to get high resolution information out of this data. So this is from the 2021 paper, from the BISECT paper, where we actually use this strategy to actually get this 3.6 Armstrong resolution. And you can see there's several steps in between that I'm not going to go over. But once you have the data in this framework, you can actually do a lot of the things that we actually do in single particle cryo-EM, exposure weighting, per particle CTF correction, and other things that actually allow you to squeeze all the high resolution information from your data. This same technique you can actually use to go all the way to better than 2 Armstrongs. This is the one I mentioned at the beginning. This is a apoferritin structure from Empire 11273, which was recently deposited. And using this type of technique, you can actually refine this all the way to, in this case, 1.8 Armstrongs. So this is just to give you an idea. This is a 100 tilt series, and this is about 30,000 particles, which is, by single particle standards, is not like a very big data set, but it's quite amazing that you can still get to those resolutions. And this will actually bring me to my next point, which is the things that are actually wrong, or not wrong, but that we still need to work on in order to make cryo-ET, a really useful and high throughput tool for high resolution analysis. So I put these numbers up here just to give people a feeling for, what are the things that we need to worry about. So in that, you can imagine for a second that you have a data set where you collected 12,000 particles, right? Which is not very big data set, it's quite small, especially by single particle standards. So we have 12,000 particles, and let's say that we use like a regular plus minus 60 tilting scheme with projections every 3 degrees, and that comes to about 41 projections in total, right? Okay, so if you wanted to do sub-volume averaging, we have obviously one sub-volume per particle, so we have 12,000 subtomograms. And if this was high magnification data, a typical box size that we would use would be 384 cube, right? So these are cubes of 384 in each dimension. So if you just do the math, just to store 12,000 tomograms using that box size, it will take 2.5 terabytes, right? So 2.5 terabytes is maybe, it's not that big, but remember, we didn't even get started with data processing here yet, right? We're just saving the tomograms, the subtomograms. And this is like a relatively small data set, right? And this is only one data set. So if you're working on multiple data sets and you have larger data set, this problem will only become worse. Now, when we use this constrained single particle tomography approach that uses the 2D projection, then the numbers look a little bit better. But you'll see that for 12,000 particles, we have 41 tilts per particle. So that's about already 500,000 projections, right? So even by single particle standards, that's like a big single particle reconstruction problem. Again, if we use the same box size, so 384 by 384, that amounts to about 270 gigabytes of just the particle stack to collect the raw data, right? We didn't even do any 3D processing. So the reason I'm doing this is just to highlight that the numbers that we're talking about here mean that you need to be very well equipped in terms of resources in order to deal with data sets that have realistic sizes. So this is, to me, it's like a small data set in a way, because it's only 12,000 particles. If we want to do in situ and look at the heterogeneity, we're going to need to have much larger data sets than this. So even storage, right, is going to become a problem. And I'm not going to talk about processing because that's, it's going to be a nightmare. But I just wanted to point this out because I think these are important problems that will need to be solved. Yes. So the title of my talk says the future of tomography. And I don't know what the future of tomography is going to look like, but I have a wish list. And these are the points that I put up here, right? Each of these are extremely important. And I think that once we solve all of these, then really this technique is going to be transformed into, it's going to become very, very useful high throughput technique for in situ structural determination. First of all, we need to routinely collect thousands of tilt series on in situ samples, right? We're going to need thousands of tilt series because, this is, as I said before, this is not purified protein, so we just need to collect lots and lots of tomograms. So unless we can routinely do that, we won't be able to advance. Next, we're going to have to develop very robust tools for particle picking. So these are crowded cellular tomograms that have lots of things in them. So unless we have really powerful tools that actually allow us to pick out those proteins from the 3D, is also going to become very, very difficult. Then we need to be able to routinely process hundreds of thousands of tomograms, not tens of thousands, but hundreds of thousands, because we want to do heterogeneity analysis. So we need not lots of particles to be able to do that. So having the tools to actually process that many particles routinely, we don't have that yet, and it's going to take a lot of effort, but I think it's going to be very important. Then we will need to get to high resolution on smaller proteins, smaller proteins of low molecular weight, not just ribosomes and apoferritin or HIV GAG, but also other proteins. We'll need to get high resolution on those. And if we have enough data and we have all these tools, we should be able to get there. And then last but not least, we'll need powerful tools for analyzing heterogeneity in situ on very large data sets. So I want to end just saying that it's a very exciting time for cryo-electron tomography, because the way I see it, there's actually three things coming together. So one is that we're getting better at actually producing these samples in a high throughput manner. We can actually collect data using BISECT or similar techniques in parallel in high throughput mode. And then if we have these scalable and robust strategies for 3D analysis, I think these are will be the three ingredients that will actually allow this technique to move forward. So with that, I know I'm almost out of time, so I'm going to finish just by making some acknowledgements. So this is part of my group. All the members are listed here on the right. The BISECT work and SmartScope was done in collaboration with Mario's group at NIHS, and Joe was the drivers in those two projects. And I just want to also acknowledge some of the the funding agencies that have, that made all of this possible. So that's everything. Hopefully there is some time for questions and we can address those. Thank you.
Thank you, Professor. Very good presentation. And I have a question about multiplexing by beam image shift. You have using 5x5 pattern. I wonder what's the high limit for this pattern? Can we use 9x9 pattern as we did in single particle procedure?
Yes, so this really is just like in single particle, right? So you can go as far as you want. Eventually you will need to worry about getting distortions.
Okay.
But we only tried 5x5. But I know there's, I believe it's NYSBC. I think they had like a 10x10.
Wow, cool.
So yeah, this is it's within the limits of the beam image shift, but you could potentially go farther away.
Okay.
Yeah. Then you get to series in 3 seconds.
Hi, this is Mahfouz Rahman from Thermo Fisher Scientific. So I have a question about, so single particle cryo-EM, as you mentioned, apoferritin is become a standard to start with. So for tomography, is there anything that everybody could reproduce and use it as a benchmark for tomography?
Yeah, I mean, I guess it depends what the goal is. If you're doing method development, maybe having something that goes to high resolution, and that's why we use apoferritin in single particle cryo-EM. So if that's your goal, I think apoferritin could be a good test. But there's many other things and many other problems that maybe doing apoferritin may not help you solve. So I don't have, I don't know what's the right answer to that. I think because we were using apoferritin single particle, then we just collected till series on those samples. But there's many things that we're not pushing the limits. I think if we just restrict to that type of test sample.
Yeah, thanks. And I have another question about, so single particle cryo-EM, the revolution was the direct electron detector, right? So what do you think for tomography is the main advancement will be in next few years?
So definitely throughput of data collection, and then scalability in the data processing, right? So yeah, we need to be in the hundreds of thousands of particles, and then we have two series of those. So we have lots and lots of problems to solve with storage and data analysis. Unless we can do that routinely, it's going to be very difficult.
Yeah, thank you. Fascinating.
Other questions? Let's get this one.
Hey, you mentioned how constrained single particle tomography can overcome overfitting. Can you elaborate on that a little bit?
Yes, definitely. So in single particle cryo-EM, right, you take an individual projection, right? And then you can determine the three Euler angles and the translation, like essentially all the parameters of the geometry, right? Now, if you do the same with tomography data, the image is going to have like a 1/40th of the dose, right? Because you had to fractionate the dose because you have 40 tilts of the same particle. So that means that one image is going to be much noisier, right? And then if you actually try to align that, you're going to fail because you just don't have enough signal in there. But when you put together the information from all the other tilts, using the fact that the relative angles between them because it's a tilt series, then you can actually recover, and then now you'll be able to align those particles to a 3D reference. So that's essentially the main idea behind the constrained single particle tomography. So if you take the data individually, you don't get anywhere because the signal is just not enough. But if you combine them together, you can actually do it. This is the same as if you do a single particle reconstruction from 100 images, it's not going to look very good. But if you build up your number of particles, you'll be able to get all the way to atomic resolution. So this is sort of like, a similar idea in that sense.
Thank you.
There was one question from online, actually two now, but the first one was, is there a missing wedge problem in subtomogram averaging, and how does this get resolved, if so?
Yeah, so there's definitely a missing wedge problem because you're not able to collect your images, in a plus minus 90-degree range. So as Liz mentioned, we usually, these days we use plus minus 60 because of the, mechanical constraints of the system. So that just means that you're not able to sample all the orientations. And what that is that, you have a problem of missing data, essentially. You don't have access to measuring those frequency components in 3D. And what that does is actually causes problem when you try to align those volumes and when you try to classify those volumes. The missing data actually gets in the way and can actually introduce bias. And some of these topics, I hope they will be discussed in the during the workshop. But it's a big problem, and it comes from the fact that the missing data actually interferes with your ability to actually align and classify these volumes.
Hi, that was a really great talk. And I guess my question is more focused on the pre-processing for tomography. Is it my understanding that's something that your lab is currently working on? Because I think that is, you made a statement that I thought was really true, that if you can't align the tilt series, then sort of like you can't do the downstream processing. And so it's sort of a waste of effort and time in many aspects of data collection. So are you sort of, if this is something your lab is doing, are you envisioning it being similar to CryoSpark Live, where you have like this pre-processing step as data is being collected?
Yeah, so we created those tools out of necessity, and I think we're not the only ones. There's definitely other groups that actually have been working on this because everybody realized that this is a problem. You need to have the feedback on the spot. So I think eventually you will be watching this live, right? So as you collect, you will be like aligning on the fly the tilt series, producing your tomograms, picking your particles. So I think this will become routine. The tools that we are developed, we are planning on releasing them. Obviously, that's the main reason why we're developing them. I don't know. I've seen CryoSpark work before. I don't know if it's going to serve the same purpose or not because tomography is very different from single particle. It will probably give you I was not a big proponent of doing pre-processing for single particle. There were very few times where we actually acted on the feedback. I think this will give you more direct feedback. It will if you can't align to cities, you stop right away and go back and change things. Yes.
I wanted to ask about if there's this, using the subvolumes is becoming less common, using just the individual tilts is more common. And in this desire to collect more data, is it better to over one day collect more data at lower tilts from 0 to maybe 48 versus collecting fewer but with these higher tilts with the ice is thicker because you're at minus 60? I'm curious how you think about that in terms of getting more volume of data and the quality of that data.
Right, that's a great question. And I think the answer, it depends what your goal is, right? What are you collecting the data for? So if you're really after, getting to high resolution, you should probably put more of your effort on the lower tilts. But you have to be mindful that the higher tilts, they're actually they're very useful for determining initial orientations and for doing particle picking, which you cannot always do accurately at low tilts. So I think it's always a trade-off, right? And being able to collect data quickly actually allows you to try out different possibilities. As of today, you just go with one strategy and hope and pray for the best. But I think if you're able to try out different things, you'll be able to optimize data collection conditions for the particular problem you're trying to solve.
Thank you, Alberto, for a fantastic talk and questions.